We had a discussion of mathematical induction. So can anyone tell me what do you mean by mathematical induction? Anyone? What is mathematical induction? Yes? What are the various steps we concentrate on in mathematical induction? In mathematical induction, we proceed with respect to a particular statement. Whatever the given statement, say for example, he has given here, let P of n be a statement which for each integer n may be either true or false. Then to prove P of n is true for all n greater than or equal to 1, it suffices to prove these things. What is the first thing? You have to prove that that particular statement is true for n value equal to 1. So that is the first required one, which you call it as the initial step, or you call it as basis of induction. Okay, and then we'll assume that the given statement will be true for n value equal to k. So given n value equal to k, we'll assume that it will be true. Based on that, we go for k plus 1. So in k plus 1, whatever the assumption we have made in n equal to k, using that approach, we'll prove that for k plus 1 also the given statement becomes true. So if you are able to prove for p of k plus 1 the given statement is true based on the assumption which is made at n equal to k, then you can say that the given statement is universally true, or you can make it as a general statement, a standard statement. So that is what a principle of mathematical induction. So like you can take an example of this. So this is a manual representation. Whenever you are going for, say for example, given. So we are given for the sum of first n. Okay, whoever joined late can just post it in the chat box. I consider your attendance. So here the given statement is the sum of first n. Now let me make it as n. First n odd positive integers is n square. Okay. Now using the mathematical induction, what we have done. So this is a general. Without using mathematical induction, we'll be checking for n value equal to 1. So for n value equal to 1, it will be only 1 because I want odd positive, n positive odd integers. So if I take one positive integer, it will be 1. The sum will be a single element. Now when I take two positive integers, it will be 1 and 3 because 2 is not an odd integer. So I directly take 1 and 3. Okay. Next, for 3 positive integers, 1, 3 and 5. For 4, 1, 3, 5, 7. For 5 positive odd integers, 1 plus 3 plus 5 plus 7 plus 9. But like this, how many elements I need to check? Okay, so there must be some limit because here there is no any limit. I need to generalize the statement. So for that reason, we go for a mathematical induction. So what is a mathematical induction? We'll be taking the basic step, then inductive step. Now based on the basis of induction, you'll be taking P of 1 is equal to true. The first one. We'll be taking P of, now n value I'll take it as 1. So first I'll take P of 1 and I'll check that whether it is true or not. Okay. Now once it is true, I'll go for the inductive hypothesis. What is inductive hypothesis? For n value equal to k, I need to assume that the given statement will be true. Then I'll go for inductive step wherein I'll go for k plus 1 and using the assumption made in the previous step, I'll show that it satisfies the given statement. Okay. So let me just go for the example. Now the same example, like say first n odd positive integers. Let me take See, don't get confused by saying the content. I'll just show it in a simple way here. Now, say for example, what is the given statement? So let me just write the sum of whatever the given here. It is nothing but the sum of yes. So it is simply nothing but the summation of first n odd positive integers. Okay, odd positive integers is asking to show that it is equal to n square. Okay, so simple. By mathematical induction, what we are going to do is first we have to check for n equal to 1. For n equal to 1, whether the statement is true or not, we will check. That's it. Okay, so for n equal to 1, what will be p of 1? Now let me consider this entire thing as p of n. Whatever the statement, that let me consider as p of n. Okay, so for n equal to 1, I need to take p of 1, which is first of one odd positive integer. What is the first odd positive integer? What is the first odd positive integer? Is my voice audible, all of you?
Yes, yes.
Okay. Now, tell me, what is the first odd positive integer? Yes? One itself. Okay. 1 is the first odd positive integer. What are the odd numbers? I'm saying positive numbers. So what are the odd numbers? Starting with 1, then 3, then 5, and so on.
7.
Okay. So the first odd positive integer is 1. Now if I ask the sum of, then I have only one element. Okay. So p of 1 is 1 only. Now what is the statement given? The summation of first odd positive integer. Yes, I got 1. Now that must be equal to n square. Now what is the n square? N value is 1. So what will be n square now? N square is 1 square, which is also equal to 1. So the summation of the first the first one odd numbers is matching with n square, where n value is considered as 1. So what we'll write here is, therefore we write that p of 1 is true. That is, p of 1 has satisfied the given statements. Okay, so the basic step is completed. Now when you go for inductive step, as per mathematical induction, now for n value equal to k, then we assume that the given statement is true. Now what is the given statement? The summation of the first n odd numbers must be equal to n square. Now instead of n, I have taken value k. So what it must be? The summation of first k odd positive integers. So first k odd positive integers means I need to go for 1 plus 3 plus 5 plus so on up to, how can I get the kth term? How can I get the kth term? First term I am getting 1. First term I am getting 1. Second term I am getting 3. Third term I am getting 5. Now how can I get the kth term? How can I get the kth term? 2k minus 1. 2n. See, if I ask nth term, it is 2n minus 1. Now I am asking kth term. Now kth term is I will be getting 2k minus 1. Okay. Because just substitute the value of k equal to 1, you get 2 minus 1, which is 1. Substitute the value of k equal to 2, I'll get 2 into 2. 4 minus 1 is 3. Now substitute the value of k equal to 3. 2 into 3, 6 minus 1 is 5. So the general representation of an odd number is 2k minus 1. Okay. So you'll be taking 2k minus 1 as well as 2k plus 1 when you are dealing with odd numbers. But here, as per the series, you'll be getting 2k minus 1 since the numbers are starting from 1. Okay. So here the summation, I need to take 1 plus 3 plus 5 plus so on up to 2k minus 1 is equal to, let me take k square. Okay. So whatever the assumption. So I'm just making, I didn't get any proof here. Remember, for n equal to 1, I'm getting P of 1 as true. It is already done. It is already proved. Now for n equal to k, I'm just going for an assumption. Now whatever I'm doing this is nothing but simply an assumption. Okay, as per the mathematical induction, I need to assume. Okay, now based on this assumption, can I prove for n equal to k plus 1, the given statement holds? Say for example, now you go for n equal to k plus 1. Okay, now for n equal to k plus 1, now what will be n equal to k plus 1? I will be taking k plus 1 odd numbers now. First k plus 1 odd numbers. So already in the previous step I have taken first k odd numbers. So let me take till 2k minus 1, which is first k odd numbers, right? So now what will be the next number? 2k minus 1 is the odd number taken. What will be the next odd number?
2k minus 2.
2k minus 1 I have considered already. Next odd number. What is the next odd number? Yes?
2k plus 1.
2k plus 1, exactly, very good. Now why? Because the next number is 2k actually in the series, but 2k is an even number. So I need to consider the next number. Okay, so in between these two numbers, I'll be getting 2k, which is an even number. So 2k minus 1 is an odd number, and 2k plus 1 is the next odd number. So for n equal to k plus 1, I am going to get this series now. Okay, now let me solve this. Now how to solve this? Now very simple. Already I went for an assumption in the previous step where I have considered this 1 to 2k minus 1. This already I have assumed that it is k square. Already I have assumed that it is k square. And now I am getting this 2k plus 1. Now I am writing this 2k plus 1. Okay. Now, can I write this particular k square plus 2k plus 1 as k plus 1 whole square?
Yes, sir.
Because a plus b whole square, a square plus 2ab plus b square. Okay, so I get here k square plus 2k into 1 is 2k plus 1 square is 1. It's the same whatever it is. Okay, so I got it finally. I got it as k plus 1 whole square. Okay, now what can you conclude now? Here, when n equal to 1 is taken, p of 1 was true. We have proved it. Now for n equal to k, we have assumed that the given statement will be true. We just went for an assumption. Okay. Now based on that assumption, now I am using this k square assumption in this. Okay, and proving for n equal to k plus 1, and I am getting the statement which is the given problem. Okay, so once I got this particular statement as true for k plus 1, now k plus 1 holds. I simply say this holds. Okay, therefore, based on the mathematical induction, directly I can assume, based on the mathematical induction, directly I can assume that. Now I'll just say based on mathematical induction. Okay, then I can directly write whatever the statement given in the problem, that is the sum of first n odd numbers will be equal to n square. Is it clear, all of you? Okay, So in the examination, whatever the problem you are taking, say for example, even if you take the sum of first n natural numbers, the same, you can apply the same. Whatever the formula is given, that you assume as the given statement, then take the n equal to 1 value, then check whether it is resulting in true or not. Then you assume for n equal to k, and then come up with some formula. Then that formula you apply in n equal to k plus 1. Okay, so this is how you need to do the problem of mathematical induction. Clear?
Yes, sir.
Okay. So after that mathematical induction, now let me move on to the next one, which is well ordering principle. Now, what is this well ordering principle? Is whenever you are having a least element belonging to a particular set, then you call it as a well ordered or a totally ordered. I'll just read the definition first. A total ordered on a set A is a well ordered if every non-empty subset B of A contains least element. Okay. Now say for example, he has taken less than or equal to. Now what he's saying, on a set A, the set A may be a set of natural numbers, set of whole numbers, set of integers, set of real numbers, whatever the set we are considering. Then he is telling that that particular set with respect to an operation is a well ordered if every non-empty subset of that particular set contains a least element. Okay, we'll deal with examples so that you can understand better. Now this is a well ordering property where we say the same given in another way. Every non-empty set of non-negative integers has a least element. So these are the examples. Now let me take the first one, the set of prime numbers. Now if I take a set of prime numbers, what is the prime numbers starting with? We start with 2. Okay. So when I take a set of prime numbers, I say 2, 3, 5, 7 and so on. Okay. Now I can't tell what is the maximum number because it is an infinite series. But I can tell what is the minimum number in that sequence. So the minimum number is 2 and that is contained in the set. So I can say that that particular set is a well ordered. Okay. Now similarly, set of finite strings over an alphabet using lexicographic ordering is a well ordered. Now what do you mean by lexicographic ordering? Maintaining a particular order. Say for example, if I take the names, then if I start as per the alphabetical order, so I'll start with A, then B, then C and so on. Like if you consider a dictionary, okay, you have that series, you have all the words which are being sorted, so that you call it as lexicographic ordering. Okay, so in that you'll be having the, say for example, if I consider the letters A to Z. Okay, so if I go on writing all the possible strings, then obviously you'll get a starting one is A. The starting one is A. Okay, I can have A, then AB, then AC, then AD, so like that. So what is the minimum one there? The minimum one is A. Now similarly, consider a set containing some elements. Go for a power set. If you consider a power set, what is the minimum element in the power set? Now, what is the minimum element in the power set? Yes? Now let me just take a set. Yes.
Null set, sir.
Very good. Null set. But let me explain again. Now let me take a set A containing elements A, B. Now can you tell me what is the power set of A? P of A, power set of A. Power set of A will be the null set, then the set containing element A, a set containing element B, and a set containing element AB. Okay. Out of this, now if I ask you, do you have the minimum element present? Do you have the minimum element present? Yes, obviously, because the minimum element present is the null set, which is an empty set. Okay. So a power set of any set is also a well ordered. Now similarly, the poset. What do you mean by poset? Yes, students. What do you mean by a poset? Which we have discussed in the previous unit, unit 2. Yes? Posets. I'm sorry, your mic is not yet cleared. Okay, good to see responses in the chat box. What do you mean by posets? Can anyone tell me? Partial ordered set.
Set with a partial order.
Yes, partial ordered. Okay, very good. So partial ordered set. Now he is asking the partial ordered set of the set given is non-negative integers with less than or equal to. Is it a well ordered or not? Non-negative integers means starting from non-negative integers. So 0 can be a positive or negative. So let me consider from 1. Okay, non-negative integers. Now I am considering from 1. So it is 1, 2, 3 integers. So I need to take 1, 2, 3 and so on. Okay, I don't know the last. It's an infinite series again. Okay, now he is asking with respect to n comma less than or equal to. Now, is it a well ordered or not? To have a well ordered, what is the minimum element of non-negative integers? Minimum element of non-negative integers is 1, and it is contained in the set where 1 is less than or equal to 2, 1 is less than or equal to 3, and so on. Whatever the element you consider from this particular set, I can relate with respect to 1 as 1 is less than or equal to any element. Let me take X in general. Okay. So I'm having the minimum element. The minimal element is contained in the given set. So I can call this as a well ordered. Okay. Now be very particular here. He has given set of non-negative integers. Set of integers. I remove the non-negative word. Now let me just say, instead of non-negative, if I just say set of integers. Now tell me whether it is a well ordered or not.
No, sir.
Yes? No. Why? Can anyone tell? Good. It is not a well ordered. Can you tell why it is not a well ordered?
We can't define the least element because it extends to minus infinity.
Very good. Exactly. Because yes, very good. Exactly. So we can't tell the minimum element what are present in the set, because if I say integer, they just start from minus infinity and ending at plus infinity. Okay, plus infinity I'm least bothered, but I want the minimal element. Now can I tell which is the minimal element? If I take minus 999,999, then some other person will come and tell some other less number. Okay, so we can't exactly tell the minimal element here. So that's why the set of integers is not a well ordered, but whereas set of non-negative integers is a well ordered. Okay. Excuse me. Now, similarly, you just go through these examples. So whatever the examples they are considered here, the following sets are not well ordered. Okay. So first one, R, which is the open interval. Now any non-empty subset if you are taking, now it is taken as R. Now what do you mean by R here? Is it a real number or rational number? Yes?
Real numbers.
Is it a R means real numbers? If I want rational numbers, then which letter will I use?
Q.
Q, very good. Okay. For real numbers, we use R, and for rational numbers, we use Q. I already used in the next examples. Okay. Now here, if I take a non-empty subset, now he has taken elements 0, 2 open interval. Okay. Now he is asking whether it is a well ordered or not. Is it well ordered or not? Obviously, it is not a well ordered, because the same reason whatever we explained just now, for the integers or real numbers, for rational numbers, all the numbers, until and unless I very specifically tell that a non-negative or positive, then only I can come up with some smallest element like 0 or 1. Okay. But if I don't specify any something like non-negative or positive, then I can't tell you the smallest element of that series. So once the smallest element is not there, then you can't call it as a well ordered. So it is a not well ordered, because he has given the same reason. The non-empty subset does not have the smallest element. Okay. Now similarly here also the poset z comma less than or equal to. Z comma less than or equal is not well ordered, because the subset of negative integers does not contain the minimal. Okay. Now here instead of z, if I use z plus, instead of z, if I use z plus, then I can go for a well ordered. Okay. Just now I was telling about the same. Here I have used a natural numbers where 1 is less than or equal to x. I can define the smallest element, but here once I say set of z, now z means including negative, positive and all. So it is not a well ordered. Okay. Now similarly for rational numbers also. Now relation less than or equal to on the set of rational numbers is a total ordering, but not a well ordered, because some subsets do not contain the minimal element. So almost the same reason for all this, because we can't tell what exactly the smallest number is in the negative series. So you don't call it as a well ordered. Now once you are having a smallest element in the given set where all the subsets are containing that particular element, then you can call it as a well ordered. Okay. Is it all clear? Now are you clear? Okay. Now let us move on to recursion, which we have already discussed in the previous unit. I'll just hope you all remembered the previous unit discussion. So already we have completed this, but let us just revisit. Okay. The same recursive function, whatever we have discussed, that we are going to. What is the time now? 1:40. Okay. We still have 15 minutes of time. So what is a recursion? Basically, when there are some situations where we can't exactly define an object explicitly. So in that situation, we go for defining the object in terms of itself. So defining a particular object or a particular concept in terms of itself is called a concept of recursion. Okay. So I did not again repeat all this. Directly I'll go for an example. I'll pass on this PPT anyway. So if you want, you can just see the same things whatever I specified in the notes which we have discussed in second unit. Okay. So whatever we have discussed, the same thing, the same point. So it is difficult to define an object explicitly, and it may be easy to define this object in terms of itself. So whatever the things we have done. So sometimes it is difficult to define, and so that we define in terms of itself. And this process we call it as recursion. Okay. Now here this point is important. The idea of a subroutine which itself can call another subroutine is common. However, it is frequently beneficial to have a subroutine that contains a call to itself. So we have discussed the concepts called direct recursion and indirect recursion. So when you go for direct recursion, the function calls itself in its function. Whereas in indirect recursion, we will be going for a function which calls another function, and that another function in turn calls this function, the first function. Okay. So in that already we have discussed factorial and Fibonacci series. Now the recursive theorem. Now here you call it as a theorem. Now what does this theorem says? It says that the first one you need to have the basic step. Whatever we have discussed, we define the recursive function is 2 steps. The same 2 steps is given as a theorem here. Now let f be a given function from a set S into S. Let S naught be a fixed element of S. Now what is that S naught? S naught I call it as the initial value of a 0 function. So that you call it as the basic step. So always remember, whenever I am going for a recursion, already I told you while discussing the concept. Now whenever I am going for a factorial, finding a factorial, then I'll be writing the formula f of or fact of n. I'll be writing as n into fact of n minus 1. Okay. Now if I go with the example with an n value as 3, say for example fact of 3. Now fact of 3, now I'll be writing as 3 into fact of 3 minus 1, which is 2. Okay. Now here 3 is already a constant, so I'll take as it is. Then again fact 2, again the same recursive formula if I apply, I'll be getting 2 into fact of 2 minus 1, which is 1. Okay. Now again this is equal to 3 into 2 into, both are constants. Now again fact of 1, again I can use the same recursive formula where 1 into fact of 1 minus 1, which is 0. Okay. Now again this is equal to 3 into 2 into, now 1 into, all these are constants. Now fact of 0, again using the same formula, again using the same recursive formula. What can I write now? I can write 0 into fact of 0 minus 1, which is minus 1. But how far should I continue like this using the recursive formula? Shall I continue for another 2 or 3 steps? Yes, students? Shall I continue the same recursive formula for another 2 or 3 steps? Where should I stop? Where should I stop? Now say this is step 1, this is step 2, step 3 and step 4. I have written 4 steps. Now where should I stop? Shall I stop for the next step, 5th step? Or shall I stop at the 4th step or 3rd step? Yes? Come on, respond. These topics are already discussed and you are much familiar. Already you have studied in your first years. Where should I stop the procedure of a recursion? So I need to stop either at fact of 1 or at fact of 0 based on the value whatever you give. If I give fact of 1 equal to 1, then I need to stop at 2nd step only. Or else if you give fact of 0 equal to 1, then I need to stop at the 3rd step. Okay. Without stopping at these steps, if I proceed further, then what is happening? 0 is getting multiplied here. Now once 0 is getting multiplied, then the factorial of 3 will become 0. Not only factorial of 3, take any factorial, it will become 0 only. So it is totally destroying the concept of factorial. Okay. So you need to have a particular condition where you need to stop. Okay. Say for example, if I say, sir, I'll say that factor of 1 equal to 1. If I want to say, I need to stop at factor of 1 equal to 1. Then I need to simply stop at this step itself where factor of 1 equal to 1, so that this entire factorial of 1 will be given as 1. Then 1 into 2. Now this particular part will become 2 and 2 into 3. So finally I will be getting factor of 3. Factor of 3 will be resulting in a value 6. Okay. So that particular condition, wherever you are giving, that you call it as a basic step or a zero function. And here he is telling the same thing. Let S not be a fixed element of S. It is a fixed. Now whether you calculate 3 factorial, whether you calculate 5 factorial, whether you calculate 100 factorial, that particular value is fixed, which you call it as a zero function. Okay. So that is placed here, right? And next, let n denote the set of non-negative integers. Then there is a unit function. Now the next step is nothing but defining the function recursively. It is based on the concept. Now if I go for factorial, I will be going for factor of n equal to n into factor of n minus 1. If I go for Fibonacci sequence, I will be going for Fibonacci sequence of order n. Or if I want n elements, then I need to depend on its previous 2 elements. That is factor of n, Fibonacci of n will be Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay. So that particular recursion. So using this basic step and recursive step, then you call that as a recursive theorem. Okay. So here it is given. The condition 1 is nothing but for the initial condition, and condition 2 is for the recurrence relation. Recurrence relation means it is a recursive step. Okay. So this is what your recursive theorem. Right. I gave some other, already we have discussed Fibonacci series, factorial, and some more examples in the previous unit. So here I give some other example. You can just go through it. Okay. Now he has given some f of 0 equal to 3, and he is asking you to find f of n plus 1 based on the formula. So now this is a recursive formula. F of n plus 1 is 2 into f of n plus 3. So based on that, I will be getting the values. Okay. Now, another small topic here, so that I'll end the class at after this division algorithm. Now, what is this division algorithm? Already you know, when I'm dividing a number, is it all clear, all of you?
Yes,
It's all
sir.
clear?
Yes, sir.
Yes, sir.
Okay, you take care of the absent. Those who are 26 is present. Any other who are present later, just post it in the chat box. I'll consider the final attendance. Okay. Now, when you go for division algorithm, it is nothing but whenever you are dividing a number by another number. Say for example, let me take 25 divided by 6. Okay. Then, now, how will you do this? I'll take okay. Now, how will you divide 6? How many times you divide? 6 1 6, 6 2 is 12, 6 3 is 18, 6 4 is 24. So the remainder is 1. Okay. Now this particular thing, whatever the given, now this I am calling it as A. Now this I am calling it as B. Okay. Now Here when I consider A and I am dividing by B, I am getting a coefficient. Now this is a coefficient. Okay. Now let me call it as Q, and this is a remainder, which is nothing but I call it as R. Okay. So can I write now this as A equal to B into Q plus R? Yes. Can I write A equal to B into Q plus R? What is
Yes.
B? B is 6. What is Q? Q is 4. 6 4 is 24 plus R is 1, 25, which is nothing but A. Okay. Now this is nothing but your division algorithm. That's all. There is nothing new here. Only thing is, now let me go for the theorem. Let A and B are integers. Okay. I have considered A as 25 and B as 6. Where B is positive integer. So B is positive. Always remember, this B, whatever you are taking is, must be a positive. Okay. A may be positive or negative, doesn't matter. Okay. Then there are unique integers Q and R such that now Q and R are also integers. Now that integers also, it depends. It depends on the value of A, whether it must be positive or negative. Okay. Remainder will be again a positive, but Q will be either a positive or negative. Okay. So such that A equal to BQ plus R, where R is lying between 0 and B. Just now I told. Remainder must be a positive compulsory. Okay. Positive means it may be a 0 also, because if it is exactly dividing the number, then the remainder will be 0. Otherwise, the remainder will be 1, 2 or whatever it is. Okay. And that particular number will be less than this particular divisor. Now this is, hope you all know the terms. This is called divisor, this is called dividend, this is called coefficient, and this is the remainder. Okay. So what will be the value of the remainder? The value of remainder, if it is exactly divided, then you'll be having a remainder 0. Okay. Otherwise, you'll have a remainder 1 or you will have a remainder 2. At most, you'll have a remainder of B minus 1. Because again, if the remainder is B, it will be exactly divided so that you get a remainder 0 again. Okay. So that's why the value of R lies in between 0 to less than B, not equal to B. Concentrate. Okay. Now, where A is divisible by B, if and only if the remainder R given by the division algorithm is 0. Now, whenever the remainder is 0, then only we can say that the given value A is exactly divided by the value B. Okay. Now, in the equality given in the division algorithm, D is called the divisor. Just now I told you. Sorry, not D here. It is B, because I have considered A and B. So, B is called divisor, A is called the dividend, Q is called the coefficient, and R is called the remainder. Okay. I'll just say it. So this particular notation is used to express the coefficient and remainder. Now, how do you express the coefficient and remainder now? Coefficient. If I ask you what is a coefficient, how will you represent the coefficient? I want to write the coefficient. So it is simply A divided by B is the coefficient. Because whenever I say 25 by 6, then if I ask you what is the coefficient, then it is nothing but 4. Okay, whatever the coefficient value is getting, I represent by A divided by B. Now if I want the remainder, then I'll be writing as the remainder R equal to A modulus B. Hope you know the percentage symbol is acting as the modulus operator. Are you all aware? Are you all aware or not?
Yes, sir.
This percentage symbol in the programming, I'm calling in the programming, you call this as a modulus operator. Okay, which is nothing but the remainder operator. Okay, so the coefficient is represented using A by B, and the remainder is represented using A mod B. Okay, so this is simple, nothing but your division algorithm. don't get afraid by using the term called algorithm. Okay, each and every algorithm is simply nothing but a step-by-step procedure of solving a particular task. So first you try to understand with an example, then go for the theorem, so that it is easy for you to understand. Okay, and give some example which represent the same. Now let me just divide 38 by 7. Now if I take 38 by 7, what will be the resultant? 38. Now 38 is the dividend. Now if I divide by 7, how many times I can divide? 7 5s, 35. So the remainder is 3. So I can write this 38 as 5 into 7 plus 3. Okay. So Q equal to 5 here and R equal to 3. Now the same thing, if I say minus 38. If I say minus 38, what will happen? What will happen? If I take minus 38, then also if I take minus 35, then I will be getting minus 38 is equal to, now can I write it as minus 5 into 7? Minus 5 into 7 is minus 35. Okay. Now plus remainder. Now if I again add some remainder, then say for example, if I add remainder 3, what will happen now? Minus 35 plus 3, I get minus 32. So I am moving away from the number. I am not coming closer to that number. My number is 38. So already I got minus 35, which is moving away. Okay. So what I need to consider in that situation, instead of minus 5, let me consider minus 6 now. Now if I consider minus 6, what will happen? Now minus into plus is minus. Okay. And 7 into 6 is 42. Now I got minus 42, but I want minus 38. Now how many elements to be added now to get minus 38? 4. Okay. Are you getting? So the algorithm, whatever the division algorithm is there, can also be applied on negative numbers. In such case, you need to consider the elements. I'll just end up in another 2 minutes. Now, in that case, you need to consider the element which is having a negative value beyond this number, so that adding some other remainder to it, you can achieve that number very easily. So I am taking minus 6 here. So when I take minus 6 into 7. Now you are not supposed to change the 7. Remember, all of you. I'm not supposed to change this 7 because 7 is fixed. This minus 38 is also fixed. So whatever the changes I need to do, that I need to do in the coefficient part and remainder part only. Okay. And already you had a condition that remainder must be a positive number. So now I can only take the negative number as coefficient. Okay. So minus 6 into 7 will be minus 42. Plus 4 will give you minus 38. So now here the Q value is minus 6 and R value is 4. Okay. Is it all clear now? All of you?
Yes, sir.
So let me just